What happens if a white dwarf star gets too close to a black hole? Can we detect such events? And can we use this to discover the enigmatic intermediate mass black holes in large quantities? Discover the answers to these questions in today's episode of my channel, Astro Edge.
Welcome to Astro Edge, weekly broadcast presenting highlights of leading-edge research in astronomy and astrophysics.
Here's the paper we'll be discussing today. The search for thermonuclear transients from the tidal disruption of a white dwarf by an intermediate mass black hole. The authors are Sebastian Gomez from Space Telescope Science Institute and Subi Ghezari from Johns Hopkins University. So we'll be discussing a few things, all included in the title of this paper. We'll be talking about intermediate mass black holes. We'll talk about white dwarfs and what happens when a white dwarf approaches an intermediate mass black hole. The result might be a thermonuclear transient due to tidal disruption. Let's first talk about black holes. Black holes come in a few varieties. The most well understood ones are so-called stellar black holes. Then there is also supermassive black holes, which we also know quite a bit about. We see them a lot. And the most enigmatic kind, the most elusive subject of today's paper is intermediate mass black hole. We know how stellar mass black holes are formed. Very large, massive stars, so-called O stars, they live very short lives, let's say 10 million years or so, and then they explode as supernova or even as hypernova, which is even more powerful than supernova. At the end of this explosion, the core of the original star may survive and collapse to make a black hole, so-called stellar black hole. The other kind is supermassive black hole. We see them at the centers of large galaxies. They're truly supermassive, whereas the stellar mass black hole have a mass of, let's say, 10, 15 masses of Sun. Supermassive black holes have masses of millions, sometimes billions masses of Sun. We see them everywhere. Every time we see a very large galaxy, chances are there is a supermassive black hole at the center. Even though we cannot see black hole itself, what we can see is its effect on the surrounding matter. For example, it can absorb and disrupt stars, it can absorb the gas between stars, and typically there is a lot of such gas at the center of a large galaxy. Supermassive black holes can gobble up the gas, make it super dense, super bright, and then we can see it glowing as visible light or maybe X-ray or radio wave. Sometimes this process is so powerful that creates super bright object called quasar. Sometimes we see jets from such supermassive black holes. In a couple of cases, we managed to see the actual shadow of a supermassive black hole. This is a galaxy Messier 87. We use powerful radio telescopes to see both the light from the gas, superheated gas surrounding the black hole, but we also see the shadow, the actual shadow from the event horizon, this imaginary boundary of a black hole. Once you go inside event horizon, nothing can leave black hole, even light cannot do that. One of the puzzles for modern cosmology is how can one make supermassive black holes? Where did they come from? Whatever made them should have been pretty fast. Using modern telescopes, we can see really far and observe early universe. Just a few 100 million years after the Big Bang, we already see there are supermassive black holes. We see quasars. How did they form? That's a big puzzle in modern cosmology. The most promising explanation is those supermassive black holes were built from smaller ones, not from stellar mass black holes. Stellar mass black holes are so small, it will take forever to build up and make truly massive supermassive black hole. There was just not enough time in the early universe to build supermassive black holes straight from regular stellar mass black holes. Instead, scientists speculated there was a way to somehow make intermediate mass black hole. And one such way I discussed in my previous episode 2. We talk about very first stars in the universe, so-called population 3 stars, and those sometimes can be so massive, maybe 10,000 masses of Sun, and they can form intermediate mass black holes. Intermediate mass black holes, they have masses of hundreds, thousands, up to 100,000 masses of sun. Early in the universe, there were no huge galaxies, only small so-called dwarf galaxies. And at the centers of these dwarf galaxies, there was just the right condition to create intermediate mass black holes. Later on, when those dwarf galaxies started merging together, making larger galaxy we see today, the intermediate mass black hole at the center of each of those dwarf galaxies would also merge and eventually make a supermassive black holes we see in the current universe. This is a convincing picture. What is missing is the proof that there are lots of intermediate mass black holes in the universe. Specifically, scientists think they should exist at the centers of small dwarf galaxies. Another important component of the paper is white dwarf. White dwarfs are end products of stars. Around 97% of stars in our galaxy and other galaxies will eventually die and become a white dwarf. White dwarf is a dead star. It's no longer shining due to consumption of hydrogen fuel. It shines because it's hot and just slowly cools down. Eventually, many billions years from now, white dwarfs will become black dwarfs, so they will not be visible at all. Normal stars like our sun, at the end of its life, will start puffing up, creating a so-called red giant star. Eventually, the envelope will just be dispersed into space, and for some time it will be seen as beautiful planetary nebula. What is left at the center is the white dwarf, the dead star. The current paper is built upon a model paper published a few years earlier. This earlier paper, back in 2016, used supercomputers and used computer simulations to show that once a white dwarf star gets too close to intermediate mass black hole, it will be tidally disrupted and will end up a thermonuclear explosion, like a hydrogen bomb. This paper describes how the explosion will look like, how bright it's going to be, how quickly it will dim with time, what's going to be the colors of the explosion, and how it's going to look like when you look at it from different directions. So the goal of the paper we're discussing today is to try to find such explosions in the archive data from telescopes. Specifically, they're using archive from Zwicky Transient Facility. Zwicky Transient Facility is a telescope dedicated for searching for such transient events, explosions, or anything which changes very quickly. They use a fairly small telescope, Samuel Ocean Telescope, to make lots of pictures of the sky every day. The special feature of this telescope that a single shot covers a big chunk of the sky. A single shot is 47 square degrees. It's roughly 13 full moons by 13 full moons, or almost 200 full moons in a single shot. That allows this telescope to take pictures of the whole northern hemisphere in only 3 days. And that allows this telescope to detect things which change very rapidly, like supernova explosions and potentially this hypothetical transient event when an intermediate mass black hole disrupts a white dwarf star. So what is the tidal disruption? White dwarf star would be disrupted by a black hole. Generally speaking, tidal disruption event happens when a star approaches a large black hole. When it approaches too close, the tidal force would start stretching the star and breaking it apart. What is a tidal force? If a very unfortunate astronaut ventures too close to a black hole, what's going to happen? Black hole produces strong gravity force. The way gravity works is the closer you are to the object, to the black hole, the stronger is the gravity pull. So for this unfortunate person, the feet would be closer to the black hole and they will experience stronger gravity pull than the head, which is further away. So there will be a differential force which would be stretching that person apart and probably killing her. Same fate expects a white dwarf approaching an intermediate mass black hole. An important conclusion in the older theoretical paper from 2016 was that if a white dwarf approaches a supermassive black hole, the ones which exist at the centers of large galaxies, it will not be disrupted tidally. It will never have a chance. It will just be swallowed by the supermassive black hole without producing of any obvious explosion. The black hole has to be of intermediate mass range between 1000 and 100,000 solar masses to produce a powerful thermonuclear explosion, something which we can detect. Going back to our paper from today, so what the researchers decided to do, they decided to take the model paper which describes how such explosions would look like. They also knew where to look for such intermediate mass black hole at the centers of small galaxies. This is where intermediate mass black holes are expected to be found. They took a Zwicky Transient Facility telescope and looked through all the data from a few prior years. So there were lots of transient things in the data. They narrowed down the objects based on their color, how quickly they become bright and then dim with time, and based on their location within galaxy. They were focusing right at the very centers of dwarf galaxies. Once they made those cuts, they ended up with just a few candidates, a few things which look like explosions from a white dwarf being destroyed by intermediate mass black hole. Here are their 4 best candidates. So as you can see at the bottom, these are the photographs of the dwarf galaxies where they found these explosions. The galaxy itself is a greenish, yellowish blob. These are small galaxies, so they're not well resolved. And the site of explosion is marked with a red cross. As you can see, it's very close to the center of a dwarf galaxy. Here at the top, what we see is how quickly the brightness of the explosion grows with time, and then we see it goes down. So the circles are the observations and the lines are the model prediction. As you can see, there is a good match between models and observations. So the conclusion in this paper that they found 6 possible explosions from a white dwarf star being destroyed by an intermediate mass black hole. One of these objects, or one of this event, was the most promising one because it looked the most similar to the model prediction. Not just the colors and how quickly it changes its brightness, but also spectral features were very close to the model predictions. So they think it's a very strong evidence of existence of intermediate mass black hole at the center of a dwarf galaxy. So they detected around maybe 1 very promising candidate for intermediate mass black hole per year of observations. That's not enough, of course. We need many more to build statistics to become much more confident. The intermediate mass black holes, they actually exist in large quantities, and they can be the explanation for existence of supermassive black holes we see inside large galaxies. Both Vera Rubin Observatory and Nancy Grace Roman Space Telescope will become operational in the next few years, and they will be able to discover hundreds times more of such transient explosive events compared to what the Zwicky facility can do today. This paper laid out a very convincing case and showed a way how one can try to find lots of intermediate mass black holes. We don't have a strong proof yet of their existence, so finding hundreds and hundreds of them would be extremely important in our quest to explain where these supermassive black holes come from. In conclusion, to solve one of the big cosmological puzzles, where these supermassive black holes come from, we really need to find lots of intermediate mass black holes. These are very elusive objects. We think there are lots of them at the centers of dwarf galaxies. We just need to find them. The paper we're covering today suggests a very promising way of finding intermediate mass black holes inside dwarf galaxies. What you need to do, you have to point a telescope at the centers of lots of dwarf galaxies and keep taking pictures non-stop. Eventually, in some locations, there will be a white dwarf destroyed by an intermediate mass black hole. Using model predictions from previous papers, we can convincingly show that what we're seeing as not a supernova explosion is not something else, it's a thermonuclear tidal disruption event because of white dwarf approaching too close to an intermediate mass black hole. So hopefully a few years down the road, we will have a very large statistics, very large number of possible intermediate mass black holes discovered using this method. This is very interesting research. In my book, it does have an edge. Thank you very much for watching. I really want to hear from you. Please leave feedback in the comments below. Let me know what you think of the material, of the coverage. If you liked today's material, please give me a thumbs up and please subscribe to my channel. See you next time.